assignment. So,
of course. So which one was it that you couldn't do?
let me see. Not necessarily that I couldn't do it, but like say part 2 for number 5, I'm not sure if I went about that one correctly at all. And then also for question 4, part C, did you mean to put NPN or was it just supposed to be
Oh no.
Not that it matters, I guess, but
no, actually it's the NP, not NPN, sorry, this is just NP. Yeah. That's a typo. Okay, so let's just begin by talking of what we were talking about. Then we can go over each one of these questions. Shall we do that?
Sounds good.
Okay, so let's now begin by actually we are doing very well, you know. One course is almost out of the way, and this other course we are doing very well considering. The last 45 minutes I just joined the academic meeting of the EE department at the main campus, and I'm glad that we're not part of them. Okay, to put it mildly. I mean, they have issues. They have far more issues than we have. Okay, so let's begin. What we said about OPAM was we basically have two very, very fundamental kind of circuits. I'm going to just draw once again to remind everyone in case they forget. So as you can see, I am plotting the same circuits over and over again. So here, right, and this is R2, R1, R2, R1. And as you can see, since this is grounded, this terminal is grounded, that terminal is virtually grounded. And here, this is not grounded, and whatever the voltage is here is almost is there. That is the point. So here is V out is minus R2 over R1 V in, and here V out is 1 plus R2 over R1 V in. Very fundamental, very, very serious, basically most important circuits in OPAM discussion. Okay, we go from there. We obviously can now decide what a summing amplifier can be. We also made this kind of discussion yesterday. Was it yesterday? Yeah. And we can design a summing amplifier that we want to sum for us, sum V1, V2, V3, V4. We can sum any number, more or less, I mean 5 numbers, 6 numbers, as much as necessary. And that would be the circuit. And if I make them all R's, then that the V out would be minus V1 plus V2 plus V3 plus V4. This is yet another summing amplifier. I can use the same circuit and call this, for example, no, that would confuse you if I call this. Let's call this 8R over 8, R over 4. That's a quarter of R, 4, 4, and 4. R over R. R over 4. No, we must make him 4R. So let me just, okay. Actually, I want to do yet another. So I'm going to make each one of these 4R, 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 and 4R. And here, my V out would be minus V1 plus V2 plus V3 plus V4 over 4, which means it's the average. So this circuit is an average taking circuit.
I'm sorry, love.
I didn't hear. Isaac, did you ask a question or was it just?
I think that was just somebody's mic accidentally came up.
Sure. Okay. So that's an average, averaging circuit. I'm just going over these because nobody asks any question. I just keep on going. I mean, if you want me to pause, please let me know if there are any questions. Then one other circuit that it is also very useful is when we have applied voltage to both terminals and R1, R2. Let me just this time call this R3 and R4 just to be different. Of course, then we can, just to see how it works. So V out 1 would be minus R2 over R1 V1. That we know. Then V prime 2 would be, this is V1, this is V2. V prime 2 would be V2 times R4 divided by R3 plus R4. And V out 2 would be 1 plus R1 over R2 times V2 R4 divided by R3 plus R4. And therefore, V out would be V out 1 plus V out 2, and that would be minus R2 over R1 V1 plus 1 plus R1 over R2 times R4 divided by R3 plus R4 V2. Can you see that? This is a subtracting circuit, but I purposely use different values of R so that you see it doesn't always have to be V out is equal V2 minus V1. Have I confused anyone yet?
No, not necessarily, but for V out 2, you said 1 plus R1 over R2. Was it was that ratio not supposed to be flipped, or is it actually R1 over R2?
I'm sorry, yes, this is 1 over R2 over R1. Thank you. 1 over R2 over R1. Thank you very much. Yes. Yes, because that is actually the ratio of the feedback. This always 1 over R2 over R1. Thank you very much. Okay, so we went this far yesterday. The other serious circuit that we discussed. Now, I'm beginning. This was all we did last week. What was it? Monday or Monday and Tuesday? Sorry, Tuesday. So today, I want to bring this other circuit that we also did, and this is called a differentiator integrator. Okay. This is an integrator circuit. So this is grounded. This is V in. This is R, and that is C. And V out is minus 1 over RC integral of dV in dt. dV in dt. Okay, that is to say, if we apply a signal there, any signal, what we will receive at that output here would be the integral of that, integral form of that. For example, if I apply a square wave there, if I apply a square wave, I will receive a triangular wave there. This is T, this is V. And we also showed that if this is plus 5 volt to minus 5 volt, this is plus 2.5 volt to minus 2.5 volt. I mean, this was only at 1 kilohertz frequency, 1 kilohertz, and we also saw the lab for it. Of course, this drawing that I just drew, that is not okay. Let me plot here to give you the actual. So I'm going to plot the input and output exactly how it should be and how we saw it in the lab. and so on. This is plus 5, minus 5. This is plus 2.5, minus 2.5. If the frequency f is 1 kilohertz, that means this period is 1 millisecond. 1 millisecond. Are we good? Right, let me now I said this, let me also say why. Why did we get the, that signal was the integrator. I see, that is R, that's V in, that is V out. Okay, I is the same I there. And I is V in over R. And V out, this V out is equal minus I into the voltage. I mean, the voltage we are measuring is the voltage across this C. And therefore is minus I x of C, which is the, if I was to write down, how can I say it so that I don't really have to spend a lot of time? Q is equal CV. If I just say C is Q over V, so are we following? Yeah. Okay. I want to take this out voltage. This is voltage across C. So here I want to say V out is I being this I, and VC being the voltage across C. In fact, VC, that is the voltage across C, is really V out. The reason being, if I was to measure V out, I would measure it with respect to ground. But since this is ground, this is also ground. Instead of measuring V out with respect to ground, I can measure V with respect to this point. That means I am measuring the voltage across this C, the voltage developed across that C. So VC is VO. Therefore, here in C equal Q over V out. And now for Q, I can put integral. For Q, I can put integral of I dt V out. So then I being, so here V out is minus 1 over RC. I'm bringing C out, integral of I dt. Yeah, okay, forget the C now. ID, that is V out is this. Now for I can put V in over R. For this, I can say V out is minus 1 over, over C, 1 over R integral of V in over C dt. And therefore, V out is minus 1 over RC integral V in dt. All right. So this is an integrating circuit. We can swap the place of R and C and get a differentiating circuit. V in C R, and V out is minus R C dV in dt. So these are the two circuits. In fact, we explored the summing, differentiating, multiplying, dividing, integrating, and differentiating by an op-amp. Taking log, taking natural log, or multiplying two voltages together. What we did this semester was just multiplying by a constant, not multiplying by another voltage. So voltage multipliers we didn't consider. Voltage multipliers are really, really hot, really hot. Voltage multipliers are those circuits that we can modulate with. You know, the AM modulation or FM modulation, you know, the FM radio, AM radio. these are you multiply two voltages, the carrier voltage and the signal voltage, either in frequency mode or in amplitude mode. So that's the FM radio or AM radio or TV signals and so on. Those are very interesting circuits, voltage multipliers, which we will discuss hopefully face to face in full. All right. So now that I believe the review, we can call it end of review session now, because we covered everything. So now let's go and solve problems on the assignment. Before we do, any questions? No, good.
Actually, I got one question real fast, going back to what you just showed.
Yep, we can do that. Right, okay.
For the, so you said V out equals 1 or negative 1 over R times the integral of I dl. Then you replaced I with a V in over C?
Yeah, because integral of, for I was V in over R. Sorry. Can you see that here? I was V in over R. and Q was CV, but then for Q, I put integral of I dt equal CV, and for I put V in over R dt equal CV out. Do you follow this?
Yeah.
So then I say, of course, with the negative sign. So V out is 1 over C integral V in dt over R. And then I call this V out minus 1 over RC V in dt.
Okay, that makes sense.
Yeah.
I just wanted to make sure. All right, thank you.
You're welcome. Believe me, the other one should have made sense. I was stupid to go away, do it different way. It should have really made sense. Sorry about that.
Oh, Professor, how did you get the negative 1 over C again?
Yeah, because it's applied to the negative terminal.
Oh, okay, then that makes sense. Thank you.
Yeah, you're welcome. Here is applied to the negative terminal. So output is always negative. So whenever a voltage is applied to the negative terminal, output is always negative. Okay. Now, seriously, I mean, are we all good so far? I mean, you don't have to be shy. I mean, this is a review. We have covered all circuits. To this, if I say for this semester, these circuits that we have just discussed are those that you need to know. But then the applications of these, obviously, you should know. I mean, the application. So before we go into solving, actually, yeah, no, we can, because one of the questions are solving simultaneous equation. So yeah, we can do that. So let me again share screen with you. So I want to go solving these assignment question. Right. Right. So let's go from the very beginning. Right. Okay, what it says here, when PN type semiconductor pieces are brought together, basically it's saying that draw the energy band diagram for each one, then energy band diagram for when they are connected together, energy band diagram under the influence of positive or negative bias. I guess that's what he's asking. Okay, so let's do this. That's not very difficult. So when we have an N-type piece of semiconductor, that is what we show as N-type, EF and EV. The semiconductor is also a P-type, that is EC, EF, and EV. When we connect them together, the Fermi level stands at equilibrium. N-type remains N-type, and P-type remains P-type, and therefore band bending takes place. So this is again EF, EV, EC, EC, EF, EV, just like the above, just like that. Now, when we forward, this is at equilibrium. This is at equilibrium. That means zero bias. Zero bias. When we applied forward bias, the Fermi level breaks down. It's no longer at equilibrium. So that is EF, and that is the EF. And then the N-type is like this. So the difference between the two EF is V forward. That is done under the influence of forward bias. And this region is the depletion region. Same here. That is really depletion region. When we reverse bias, this Fermi level goes up there, this Fermi level remains down here, and now that is N-type, that is P-type, and as you can see, the gap is much greater, and therefore the difference between the two Fermi is the reverse voltage. So EC, EF, and EV, EC, EF, and EV. If everybody is good, we can continue.
I just have one question. So are these are our energy diagrams, right?
These are
Or-
energy band diagrams, yes.
Okay. I mean, we're gonna go over it, but like, what's going to be the difference between this and then the question 4, where it's also wanting energy diagrams?
Question 4, question 3, question 4.
It says after, the Fermi levels have
So what-
equalized, and then
I
forward.
didn't, what is this question? Okay, sorry, I misread the question maybe. PNN semiconductor brought into free electrons. Oh, is asking for depletion region. Says, okay, create a zone devoid between the charge carriers called depletion region. What happens to the thick? I'm sorry. What I just did with the solution to question 4. I'm sorry, I should have read the question.
So is number 1 going to be like if we literally draw our N-type and our P-type
Yeah.
piece, and then just show the little region in between them growing and shrinking?
Exactly. Let me do it. Yes, I'm sorry about that. I should have read the question before. That was wrong. So this is really not the solution to question 1. Good job, Israel is awake. So what the question 1 is asking is saying that if we have 2 pieces of semiconductor N and P, this depletion region that is created between them, which is depleted, or as it says, devoid from the carriers. Then what happens if we apply, for example, forward bias? To what happens to this depletion region when we apply forward bias? Okay, that would be what's happening if we apply forward bias. Sorry about that. V forward. Depletion region would look like this. And if we apply reverse bias, depletion region would look like this. V reverse. And by V reverse, if this is N, this is P, I mean, this is reverse bias. Oops. Come on. What is going on here? All right. So this is V reverse, and that's V forward. That should have been this. This is the answer to question 1. I'm sorry about that. Okay. So now we can go to next question. Question 2. I will read the question from now on, so I won't make it up, make a mess. The relationship between voltage and current for a PN junction is described by this equation, which is this equation here, sometimes referred to as the diode equation or Shockley diode equation after its discovery. Then it's defining each, it's actually defining each term, which I'm going to do for you now. What's going on here? And then the question is, at first this equation may seem very daunting until you realize that there are really only 3 variables in I, D, V, D, and T. All the other terms are constant, since in most cases, so it's asking basically what is the relationship, how we can simplify, right? We are really only dealing with 2 variables, diode current and diode voltage. Based on this realization, rewrite the equation as a proportionality. Okay, that I understand what the question is. So now let me go over and solve it for you. What he's saying is just telling you that ID is equal I0 E Q VD KT minus 1. Might have a constant term before, or NKT, putting NKT. Some call it, let me write it down here, E to QVT, some call it eta KT, some call it, as this term has shown, QVT divided by N KT. This term, N or eta or N for silicon is 1. So we don't normally put that there. For other materials, it changes. So that term, that's why in this relationship, we don't normally include it. Because the eta is normally for silicon is, sometimes it's 1, sometimes it's 2, but it's for our purpose, it's always 1. Okay? Now, let me make sure that nothing else is said. So ID, IS, Q, VD, N, non-ideality coefficient or emission coefficient, typically between 1 and 2. That's right. That's what it says. Boltzmann constant and temperature. Right. Okay. So when we say the current through diode is some constant current, which is called the leakage current or constant current, exponential Q VD over KT should have said VD here. Minus 1. Right. Since I0 is a very, very small constant value, this I0 is in the order of nanoampere. Is in the order of nanoampere. And it's for specific diode is a constant value. It does not change much. Although it's very, very marginally temperature dependent. However, it doesn't change much. So we can take it as a constant. So I can write down I equal a constant times an exponential term, which is Q VD over KT minus 1. Now, if I would put Q is equal 1.6 times 10 to minus 23 Coulomb per second. Sorry, it's just Coulomb. I'm sorry, not per second. Just Coulomb. If I just put 1.6 Coulomb. And if I put K is 1.38 times 10 to minus 23 something. Let me look it up. Let me see. Oh, it doesn't give the units, but it's, I can't remember what the unit is. Anyway, it's 1.38 10 to minus 23. And if I put T as 300 Kelvin, see, 300 Kelvin means it's 273 plus 27 degrees C. 27 degrees C is room temperature. And because 0 Kelvin is when we are, in fact, the degrees C must be added to 273 in order to make it into Kelvin. So we always, in all problems, we take room temperature as 300 Kelvin, just a round figure. So if we put all these values, what we will get Q divided by KT equal 26 millivolt. In fact, the actual value is 0.0258 volts. If we put the real values, I mean, the exact values is like this. We call this 0.0258. We call it 0.26, which makes it 26 millivolts. So you must remember this. I'm sorry, there's no way about this. Q
Yeah,
of a
Professor?
Yeah.
Yeah, because I mean, I'm sure we all know by now that that's always going to be 26 millivolts, but
Sure.
say we do put into the calculator, I just myself, I can't ever really get that value. I
No,
get
because-
something like 38.
Exactly, because of this fella. This, we have to get the units right in order to make it in terms of Coulomb and Kelvin temperature. This is, if I honestly can't remember for many, I don't know how long it is. This, if we get it the right unit, this will get to 26 millivolt, yes. What I will do for you again, for the third time, I will promise you, I'm going to write on my wrist now, to get you that graph that I was trying to get you, and also this, and I will email it to everyone. So today, I will send you one page just to get these values right, get this constant right, multiply, divide, and all this, and also get that graph that I was telling you about. And I will put them on one sheet of paper and email it to everyone. Would that be good?
That sounds great.
Okay. And all right. You know, we have been unnecessarily preoccupied with this board of advisors meeting, which is tomorrow night, 6 o'clock. There are almost 30 people attending, and I honestly are preparing PowerPoints and presentation and inviting these people. We are also we are employing a director for the program. We're hoping this director will start, the director in the place of that Dr. Dejani. Remember, you guys were here when Dr. Dejani? No? Okay. Dejani left just before you joined the program. Initially, the program, when we started in 2011, it was Ken Central